So it's now is recording. Yeah. We already received some sign that it's recording, no? Up. Cool. So, well, I think we can start now, and still people entering, but just to be on time, I want to welcome everybody to our first rock glacier inventories and kinematic service workshop seminar. And for this occasion, we have Lynn Rouyet. And Lynn has been working in the action group with us since the beginning. She has been involved, especially in the kinematic area. Now it's called velocity, because probably she can tell you later why we are calling now velocity and not kinematics. But it doesn't matter. She's great. She's working in the Norwegian Research Institute in Norway. She's originally from Switzerland, and I think I can leave you now to start your presentation. And questions, we have 20 minutes for the presentation, more or less, and then we will have some 10 minutes for discussion. And if people is still interested to further ask questions, we will set up a channel in Slack. If you know on Slack, I will post a link to make sure that you can get to Slack, and then you can ask further questions in the Slack or discussions. So all for you, Lynn, and thank you for giving us the presentation.
Thank you very much. So you can see the screen and hear me well? It's fine? Yes, okay,
Yeah.
cool. I will try to keep track of the time, but in case I'm too long, just cut me, and we can also take more question and discussion after. It's not meant to be a really long lecture. It's more like introducing a bit what we have done in Norway with these rock glacier inventories, and how we used synthetic aperture radar interferometry to add an information about rock glacier velocity, as it is called now. So it's I've been the one presenting today, and in the mail it was shown as the Lynn Rouyet seminar, but actually it's a big group of people involved in this process. Some colleagues also from North, so the institute I'm from in Tromsø. Also people from the University of Oslo, and some people from the University, Central of in Svalbard, in Longyearbyen. And so this project is part of bigger initiatives. So the result I will present today. Most of the inventories have been made thanks to the funding from the European Space Agency Climate Change Initiative Permafrost, CCI. So you can also look at the link. And it was a little add-on project, part of this bigger initiative that we're focusing on mountain permafrost and rock glacier inventories and time series monitoring. And it's also a lot of synergy with the IP Action Group, because both initiatives started a bit at the same time, and then we also use the work done in the IP Action Group to design these guidelines that can be applied in the CCI project. And just to let you know that so this option, so this little project that was focusing on rock glacier within CCI permafrost, actually had much more than Norway. So we had 11 regions in total that we studied. And now there is a paper that is currently in review, but already available as a preprint in the cryosphere, led by Aldo Bertonna, that is giving an overview about the result for these 11 regions. So you're really welcome to have a look and also comment. It is not published yet, so we are happy to get a feedback about it. And the goal of the entire project was to exploit satellite remote sensing to scale up the investigation of rock glacier and generate inventories at the regional scale, but in different regional setting. and then document the movement rates of this rock glacier all around the world, as you can see on the map. And also one part was to evaluate the potential of using rock glacier velocity as an associated parameter of the essential climate variable permafrost. So using time series. But today I mostly present results related to the inventories. So it's a snapshot and we like mapping the mean velocity over several years. I will not spend too much time explaining the work that we have done related to the time series. For Norway, so you see on this map with the 11 regions, we had 3 regions or area of interest. 2 were located on the mainland in northern Norway, in Troms and Finnmark, and 1 was in Svalbard. For the inventory in Troms, this is a paper that has been published last year, so you're really welcome to have a look for more detailed information. The Finnmark inventory, it has been included in a paper that is also discussing wider questions, but it's currently in review and also available in preprint in Earth Surface Dynamics. So you're really welcome to have a look, and same comment that before, it's not published yet. So if you have any feedback to make, it's not too late, that we can maybe improve the manuscript. And the Svalbard inventory is not published yet, but we are planning to do so in the near future. So there are many techniques that can be used to document kinematics, of course also in situ based. But this CCI project, because it's funded by the European Space Agency, the focus is to use satellite remote sensing to upscale the analysis. And in this case, we focused on one technique called INSAR, a synthetic aperture radar interferometry, where we compare images taken at different times and radar images to detect movement. So if you have the satellite coming on day 1, and for example, using Sentinel-1, that is a European satellite, it's coming back 6 days after at the same location. And by comparing these 2 images, you get an information about the displacement that occurred between these 2 time acquisitions. One important thing to remember is that you have, like, if you have this rock glacier creeping down slope, you have the black arrow here is the real displacement of the rock glacier, and what we can measure with INSAR is the displacement occurring along the line of sight of the radar sensor. So this is what is shown in red. So we, in this case, slightly underestimating the rate. And then you can, of course, look at this as a map. So you can map the displacement by doing exactly the same, but having a spatial information on how the displacement is distributed along the landform. And for if you just consider 2 images, you get quite high sensitivity to displacement. With you can detect millimetric to centimetric displacements. But of course, we know that rock glaciers are moving at really variable rates, from some centimeters to several meters. So we need to have quite a large range of detection capability. So one way to do that using INSAR is to consider several images with different topol intervals between these images to cover a large range of velocity. So that's what we have done in these projects, where we used hundreds of images from several years in summer, because one limitation of INSAR is that it cannot work on, it doesn't work on snow. So it's images between June and September, October, typically. And then we generate pairs between these images with different intervals, 6 days, 12 days, 18 days, until a year. And also we use two different geometries, so different kind of viewing angle of the satellites, and to kind of overcome this limitation I spoke about before related to the line of sight. So using the entire stack of information we have from Sentinel-1, this satellite, and using many pairs from many years, then you can get an overview of the mean annual velocity from millimeter to meter, and document different kind of landforms, basically. And then we summarize the information we get from this analysis, and classify the mean velocity according to the classes recommended by the IP Action Group. So there is a document on the web page of hosted by the University of Fribourg that it is called kinematic as an optional attribute in standardized rogue glacier inventories. That is recommended to have this half order of magnitude creep rate information. So 1 to 3 centimeter a year, 3 to 10 centimeter a year, 10 to 30 centimeter a year, and 30 to 100 centimeter a year. So that's what you see a bit as an information on this map. And we classify according to these classes. We added also a lower classes, because with INSAR you can get quite good sensitivity to low velocity. And then we finally merge all this information into an INSAR velocity map that is summarizing everything that is moving at the regional scale. So not only rogue glacier at this stage, but everything that is moving. So this is the kind of product you can get. This is for the area of interest 1, so in Trums, the inventory that has been already published. And you get this kind of simplified INSAR products where you can quickly identify where something is moving with these 6 classes. So everything that is transparent is under the detection limits of 0.3 centimeter a year, and the other 5 classes are significant velocity. It's a semi-quantitative velocity information. And then in addition, we also added three classes that shows where we should be careful. It's not because there is no information that it's not moving, it's also because there are some interesting limitations in INSAR technique. Because of this line of sight problem, by example, north and south facing slopes cannot really well documented. So there is a mask that is shown here in blue, showing that you cannot really trust that in this area nothing is happening. And the same for the black mask here that shows where actually we don't have any information because of shadow effect. And looking already like really broadly of this map, you can see that these polygons in black are where it was mapped a previous landform before, either a rock slide or a rock glacier. And you can see that some of the moving areas are fitting with an identified landform at several locations. And then, of course, at this stage, we have just moving areas. So it's not a rock glacier inventory, but luckily in Norway, we had from before quite comprehensive inventory of rock glaciers and ice core moraines over the entire mainland. So not in Svalbard, but in the mainland. That was based on morphological evidences, so mostly aerial orthophotos, basically. And what we did was to overlap the morphological inventory with this INSAR inventory we made, and to assign a kinematic attribute to the morphologically inventoried landforms. So in a way, we move from a morphological inventories to a morphokinematic inventory. And in addition, we also updated the inventory. So we refined, revised the delineation, and also thanks to INSAR, we discover 54 landforms that were not inventoried on previous in the previous database because of the quality of the orthophotos or shadow effects, snow, whatever, but that were quite clear. Typically, this example here, the example 3, where we could see really a quite clear signal from INSAR, and when looking at the orthophoto, we indeed see that something is happening here. So in 54 landforms were discovered in this region thanks to that, and in addition, in some other areas, we had previous inventory that was quite vague, including a landform that exists and is clearly visible on the imagery. But when looking also both morphologically and based on INSAR information, you can see that there are actually different units. So we separated this unit. The same here in that case, where it was actually an entire landform that included also a relic part, but with quite active little lobe on the top of it, and several actually. So then at the end, we can start to make some statistical analysis about these results. That was not so much a purpose in my work, actually. So we didn't go that far with how to exploit the data we have now. So you're really welcome to use the data if you think it's interesting, because I believe we could do more. But basically, you have here all the units that have been identified, classified by the kinematic attribute measure with INSAR. And we can see there is a quite large variability of creep rate. And also there is a quite clear spatial pattern with western part dominated by non-moving rock glaciers that are identified as relicts. And then it's more active in the interior, which fit with the expectation. It was partly also showed in the previous morphological inventories that this landform here are relics. Oh, somebody has to mute, I believe. There is a big, yeah, okay. And if you map along a profile that is running from west to east, you see also the different a trend in elevation and this trend in terms of relic to active landform when it's cold, because it's colder in the interior. Basically, there is still permafrost in the interior, while the western part is mostly non-permafrost today. Then I will just show some another case, so the one from Svalbard, briefly. I thought it was interesting also to speak about Svalbard because in that case it was a bit a different process. We had to start from mostly from scratch because in Spitsbergen we didn't have a morphologic rock glacier inventory. Before we started the project, but we had UNIS was on board, was part of the project, so they had as the main task of UNIS was to do this morphologic inventory before we actually started to add a kinematic attribute in there. So they did this work and mapped rock glacier based on recent aerial imagery and also some historical sources. So some people had started to inventory the landforms. And they also followed the recommendation from the IP Action Group to classify them by spatial connection, activity types based on the new categories. So you see here one example of talus connected and one example of glacier connected, typically. Then we also did this INSAR processing. This is quite challenging in Svalbard because basically everything is moving in Svalbard. It's a continuous permafrost environment where you have in the flat terrain, you have soil subsidence during the summer due to melting of ice in the active layer. So all the red areas here in the bottom of the valley are not rock glacier, obviously. This is soil subsidence. So this map again is showing much more than just rock glacier. It's showing everything that is moving in a way or another. So then we had again to clip or to extract the information that are to focus on rock glaciers. And here you have just an example around Longyearbyen, the main settlement in Svalbard, with different landforms that have been mapped. And this is the statistic for the moving areas. It doesn't. It is each pixel of the INSAR map documenting mean velocity. So it's not the kinematic attribute that is assigned to the unit. If then you kind of summarize information you get for each landform, you can start to have a more general information about the creep rate or the rock glacier kinematic attribute. And here you have the final map regarding the kinematic attributes. I'm soon done. I see I'm kind of soon out of time anyway. So that's just a quite short introduction to show that in this project, the goal was really to combine both geomorphological interpretation and INSAR kinematics to move from morphologic inventories to morphokinematic inventories, and to further understand distribution, activity, and behavior of rock glaciers in polar and mountainous regions in Norway. And as I said, it has been done in several other regions around the world. So you're really welcome to have a look at this article from Aldo Bertone. And another part of it that we have started, but it's let's say a bit the next step. I would rather say this way. There is still a lot of work to do for that. Is to move from mapping the landform to the monitoring of selected landforms. And this can be used as indicators of climate change, as we know that warming permafrost tend to lead to an increase of creep rate. And so the next step would be to select several landforms, like you can see on the bottom left, generate time series. So this is a time series that is really for each pair of images based on INSAR. And then we'll have to average this information by season or by year, and then average several time series and several landforms to make regional indices that can be used as an indicator. And this could be potentially done nationally, of course, but also in many regions, so all around the world. Yes, I think that was it. I don't have more. Yes.
Thank you very much for the presentation, Lynn. Was great. So now I think we have time for a few questions. Also, I posted if you you can give us all the links to the publications that you show, especially the ones